Welcome to Introduction to Programming. My name is Steven.
And my name is Sean.
Over the next 90 minutes, we'll be taking you through this series consisting of 21 different segments that hope to cover the basics of computer programming, which can apply to any and all programming languages you might want to learn. We'll be starting with the simplest question of what is programming, and from there, we will be working our way up as we talk about common features of computer science such as loops and arrays. We'll discuss how to read and write code, debug code that you've written, some strategies to help you plan out your code, and much, much more. The complete list of topics that are going to be covered in this lecture-style video are shown on the screen now. Additionally, there will be timestamps in the description, so feel free to skip around if you are already proficient in some areas of computer science or just want to know about a specific topic we will be covering. Hopefully, by the end of the series, you'll have a basic understanding of what computer science is, along with an armory of useful skills that will help you unravel whichever programming language you decide to learn first. We'll only be covering the major key points that apply to all programming languages, so we'll be shying away from topics such as object-oriented coding and command line navigation, as those are things which are language specific. Additionally, there will be no software required for you to download in order to follow along with this tutorial, as we won't be writing any code in an IDE to keep things simple and concentrated. This video is meant for those who are interested in computer science and programming but have no idea where to start and have little to no background information on coding. And so if that sounds like you, then strap in as Sean and I work our way through the wacky world of computer science, starting with the biggest question probably on your mind, which is what even is programming?
Well, the dictionary defines it as the process of preparing an instructional program for a device. But that's a really confusing definition. So, in layman's terms, what exactly does that mean? Essentially, it is attempting to get a computer to complete a specific task without making mistakes. Imagine this, for example. You want your less than intelligent friend to build a Lego set, except he has lost the instructions and can only build based on your commands. Remember though, your friend is far from competent, and so if they are not given very specific instructions on how to build the set, there are many mistakes that they could make. If he thinks like a computer, then if there is even one piece that you have not told him specifically where to place and how to place it, the entire Lego set will be ruined, and he will be left to suffer a complete mental breakdown, causing the whole goal of the project to be corrupted. Giving instructions to your friend is very similar to how programmers code. Instead of a less than intelligent friend, you have a less than intelligent computer. And instead of instructions on how to build a Lego set, we are feeding it information on how to complete a program, like a game or a web application. An important thing to note is that computers are actually very dumb. We built them up to be this super sophisticated piece of technology, when in actuality, a computer's main functionality comes from how we manipulate it to serve our needs. Now, programming isn't as simple as giving your friend instructions, since in a programmer's case, the computer doesn't speak the same language as you. The computer only understands machine code, which is a numerical language known as binary that is designed so that the computer can quickly read it and carry out its instructions. Every instruction fed to the computer is converted into a string of ones and zeros, and then interpreted by the computer to carry out a task. Going back to the Lego example, this process would be like if he was not only less than intelligent, but to make matters worse, he could not understand English and only speaks in Mandarin Chinese. In order to speak with him, you have to convert the instructions that you understand in English into the language that your friend understands. This process is essentially what you must do for your computer in order to make it understand the instructions that you give it. The big difference between the two examples, however, is that it is very difficult for people to understand machine code in binary. Directly translating what you want the computer to do into machine code is extremely difficult, in fact almost impossible, and would take a very long time to do it if you could. Each program is composed of millions upon millions of those ones and zeros, so how, exactly, are we supposed to translate our instructions into machine code? This is where programming languages come into play. Programming languages are fundamentally a middleman for translating a program into machine code. These languages are much easier for humans to learn than machine code, and thus are very useful for programmers. Going back to our Lego example, a programming language would sort of be like an interpreter that's able to take the instructions you give them in English and translate them into instructions your non-English speaking friend can understand. This makes programming languages extremely useful and the backbone of any good program. Think of programming languages as not English and not machine code, but somewhere in the middle. There are many different programming languages out there that each have their own unique uses. Languages such as Python and Java act as general-purpose languages that can perform a variety of computational tasks, while Robot-C or HTML or CSS are languages designed for more specific purposes, such as moving a robot or constructing a website. Languages can also vary in how powerful they are. For instance, JavaScript is a scripting language that is designed for smaller tasks, while Java or Python can carry out much more computationally taxing processes. We can measure a programming language's power, or level, by how similar it is to machine code, the series of zeros and ones we talked about earlier. Low-level programming languages, such as assembly or C, are closer to binary than a high-level programming language, such as Java or Python. The basic idea is that the lower the level of your programming language, the more your code will resemble what the machine can interpret as instructions. Aside from the different purposes that each language fulfills, choosing a language typically comes down to a matter of preference, as there are usually many languages that can accomplish similar tasks. Try different languages and decide which one's rules, interface, and level of simplification you like best.
So now that we know what programming is, how do we actually write code? It's not like we can simply type words into a text document and automatically assume that the computer can translate it into machine code, read it, and carry out a task like opening up a browser. And additionally, we can't just write down rubbish in certain programming languages mentioned in the previous segment and expect the computer to understand. So how are we supposed to write code then? Well, the answer is with an IDE. An IDE, which stands for Integrated Development Environment, allows the facilitation of code by a computer. IDEs provide a graphic interface on your computer in which the programmer can easily write, run, and debug code without having to worry about problems with complication or interpretation of the program. Think of an IDE as any other program on your computer, such as a game, a browser, or even the File Explorer, except we'll be using it to write code. IDEs are able to turn your code into machine code and run it through the computer to produce results. In addition to providing a place for programmers to develop their code, IDEs provide some extremely useful tools for programmers to ease the job of writing code, such as built-in error checking, because as we'll talk about later, code doesn't always run correctly, autofilling for frequently used words or phrases, and a project hierarchy, which will help you organize and manipulate the files within your project. Back in the olden days, before IDEs, code used to be written on punch cards and then fed into computers, which would take hours and cause a lot of pain. IDEs nowadays act as sort of a fast track to writing code and make things a whole lot easier for programmers. An example of a specific IDE can be seen on your screen now. In the center you can see the program that is currently being written, and right below it is the console, which can print out useful information for the programmer. This specific IDE is used to write Java code. IDEs are extremely powerful and will be used in almost 100% of your programming projects. So through these IDEs, we are finally able to write and compile code smoothly without worrying about the computer not being able to understand it. The next problem we run into then becomes how do we write this code in the IDE? Because it's not like we can just type random words from a certain programming language and expect the computer to understand. This is where a programming language's syntax comes into play. Now, just as if you were learning a real language, learning a computer language can be very similar. Some have different styles that may seem odd, some may make you use weird or abstract concepts which may be confusing, and like all languages, programming languages have a set of rules that you must follow when writing code in that language, and at the forefront of those rules is grammar. Programming grammar is referred to as syntax and is very similar to real-world grammar. Each programming language has its own syntax or rules that you have to follow to a T if you want your program to run correctly, just as if you were speaking in real life. These can be things such as how you type out certain functions, what you put at the end of a line of code, and how you set up certain functions. Each language is unique in its syntax, and while some may share similar rules, all will have some quirk which makes it stand out from the rest. Syntax is something that catches a lot of people off guard, since many expect every programming language to follow the same set of rules. But as we spoke about in the last segment, because each language is specialized for a specific task, each needs its own set of rules to function. Breaking or disregarding these rules will result in an error, just how breaking or disregarding rules in real life will result in an unintended message. As an example, if you wanted to do something simple such as initialize a variable, which is something that we haven't covered yet, but the example is still relevant. In Java, you'll notice how we have to specify what type of variable we are defining, in this case an integer, and also add a semicolon after the statement. In Python, we don't even need to define that we are trying to create a variable and just have to type what we want to create. And in JavaScript, we just specify that we are making a variable, but we don't include what type of variable we want to make, like in Java. Even in this simple example, you can see how much a syntax matters when learning a new language, since while the goal of our program remained the same, which was to define an integer with the value 3, all the programming languages shown took different approaches. All these languages require that you follow this syntax because remember, computers are extremely dumb. If you forget one semicolon or misplace a character, the entire program will not run and send you back a syntax error, which is something we'll talk about later. Think of this as if you forget a comma in a sentence and the entire context of what you're trying to say gets misinterpreted. For example, in the sentence, "Let's eat, Grandma," if you were to forget that comma, while it may seem like a small mistake, it changes the entire context of the sentence, making it sound like you're going to eat your grandma. The same rules follow for programming. If you forget a semicolon, the entire context of your program could be corrupted and misinterpreted by the IDE. Now, another thing which makes IDEs so useful is that they will let you know if and when there are syntax errors in your code. Syntax errors, of course, being parts of your code which do not follow the same rules what we talked about previously. The IDE will tell you where in your code the error is, and also won't let you run your program until the error has been fixed. Because of how important syntax is to writing code and learning a new language, it's recommended that you learn the rules and syntax of a language before beginning to write complex programs in that language. Most of the rules are tedious to learn but easy to master, and as soon as you can do that, you'll be able to easily identify syntax errors and take care of them easily, and be writing code in no time.
That covers the basic gist of syntax and programming rules. So now that we know how to write code and where to write code, we next need to cover what happens after we have typed out our program and run our code. Because writing a piece of code for a game or for a database is cool and all, but after the computer interprets the program, how will we know what's happening and whether or not it is working? Well, programmers do this by looking at the console. The console is a text interface within your computer that us programmers can use for a variety of different purposes. If you remember, a short while ago we showed a picture of a basic IDE, and one of the main parts of the picture was the console. The main use of the console is to output text from the program. This is usually done by using a print statement. A print statement is a command that does exactly what it sounds like. It prints text to the console. The print statement is the first piece of actual code we've talked about in this series, and it's about as simple as it gets. The print statement, despite its simplicity, is one of the most important functions in programming and exists in some form in just about every programming language. The most basic thing you can ask the print statement to do is to just simply make it say something. This is done by instructing the console to print, and then include whatever you want to be printed inside the parentheses. For example, in Python, the segment of code print hello world will cause a message reading hello world to appear onto the console. Pretty neat. The print statement is also vital for viewing and interpreting the computer's output from a program. For instance, if you tell a computer to run a simple calculation, for example to determine what 4 plus 3 is, it will run the program internally and compute an answer. However, what is the purpose of having the computer run this program if you will not be able to tell what the result is? Instead of simply telling the computer to perform this calculation, instruct the computer to print the output of the program to the console, and upon the program's completion, 7 will appear on the console. As you can see, the console allows us to easily print information out to the developer for a variety of uses. It is important to note that the print statement varies depending on the programming language being used. For example, in Java, there are multiple versions of the print statement depending upon whether you would like a line break after the printed text or not, as well as specialized print statements which make your code run more efficiently. Also, the general syntax of using a print statement and certain nuances of its function can change between languages. However, you can generally rely on it to carry out the same overall function, as it is a foundational statement for programming in general. All of its functionality makes the print statement, along with the console, a very useful developer tool. However, it is important to remember that that is all it is, a developer tool. The console is not really meant to be viewed by the end user of your program. It tends to be hidden away behind the scenes, and other methods of displaying information, such as displaying text, graphics, or images, are used to convey information to the user instead. Think of it like this. When you are using your phone, you see the console in none of the programs you use. So while you can use the console to give yourself information about how your program is performing, don't try to implement it into the final product because it fundamentally just isn't meant for that. Overall, remember to use the console to its fullest extent when writing and fixing problems in your programs, as it is a great tool to use to tell how your program is performing behind the scenes.
So now that we know a bunch of information about programming languages and how and where to write them, along with the print statement under our belts, let's go over some intuitive things that the computer can do all by itself, without you having to tell it how to. More specifically, we'll be covering some basic number mathematics, as well as string math. Starting off with basic mathematics, the computer already knows how to do simple arithmetic. This includes addition, subtraction, multiplication, and division, all of which are represented by the symbols shown on the screen now. In any IDE that you may install, you'll be able to print out the answer to simple math problems using the print statement, which may seem counterintuitive because why would you use the computer to do math when you have a perfectly good calculator on your phone? But you have to remember that computers are dumb, and anything we want a computer to do, we have to build up from scratch. Basic arithmetic, while simple, helps out in almost any program you may write. For example, if we wanted to build a basic calculator app, we'd need to utilize this functionality in order to correctly display the answer to an arithmetic problem when our user tries to add, subtract, multiply, or divide two numbers. Now, in addition to the 4 basic math equations, most programming languages include an additional operator known as modulus. If this is your first time hearing this word, don't worry, since it's not usually taught in math classes. Modulus allows us to get the remainder of a divisional operation. For example, when we take 10 modulus 3, we are essentially telling the computer to take 10, divide it by 3, ignore the actual answer, and just give us the remainder of the operation, in this case 1. Since when we divide 10 by 1, the answer is 3 remainder 1. The 1 in this case is what gets printed out to the console. If there is no remainder, say in the case that we take 50 modulus 2, since the remainder is 0, the function would return 0 if we were to print it out to the console. This can be extremely useful in many cases, the most obvious being if we want to determine whether or not a certain integer is even or odd. If we take a certain number, modulus 2, and it returns 0, then we know that is even, because any number divided by 2 will always result in a full answer without a remainder. But if the system returns 1, then we know that the integer is odd. You will find yourself using the basic math operators a lot more than you think, so it's good to keep them in mind when writing your program. Now, not only can our computer work with numbers, but it can also work with strings. Strings, by the way, are just another way to say text. For example, hello world is a string, the letter A is a string, and anything enclosed by quotation marks is denoted as a string in programming languages. We'll cover more about strings in a bit when we talk about variables, but for now, let's continue. We already talked about printing strings to the console, but let's say we're making a game, and we wanted to print out the statement, game over, 4 was your final score. Now, while we could just make a string that says that exact phrase and print it out to the console, in some cases it would be more useful to print out the actual integer value, especially in the case of a game where the score can change each time you play, because score definitely isn't always going to be 4. Well, we're also able to print out multiple strings of text, and even integers, by adding them together in the print statement. This is known as concatenation. Continuing with our score example, if we wanted to print out the statement, game over, 4 was your final score, using 4 as an integer rather than a string, we could do this by breaking down the statement into 2 strings and an integer like so. Print game over plus 4 plus was your final score. We of course begin with the print statement, which again will be different across all languages, but in this case we're using Python. Inside the print statement, we start off by printing the string game over. Now here comes the important part. From there, we use a plus sign and add 4 to the print statement, just like if you were adding 2 numbers. Then we can repeat this process with another plus sign for the final string was your final score, and we're able to print out the entirety of our statement easily. Doing this, we can easily print out multiple different strings and integers together in one print statement. We could also combine the 2 lessons we've learned thus far and do something such as game over plus 4 plus 4 plus was your final score. In the case, let's say, where you have a game which gives you a base score and then 4 points for a certain task that you completed. This demonstration also displays another important part of programming, which is that oftentimes, to get your program to be the most efficient, you have to combine aspects of code. Now, it's important to note that the computer will take whatever you put in the parentheses and print it out, character for character. So oftentimes, programmers will forget to add a space onto the end of their strings. This can result in a small mistake in which the string from the previous example would be printed out as if to say, game over 4 was your final score, which isn't that appealing when displayed on the screen to the user. So it's a good practice to always put a space after and before your strings to make sure this doesn't happen and your string doesn't end up like that. Another important thing to note is the difference between for in quotation marks and for without quotation marks. Now, for in quotation marks is treated as a string rather than a for without quotation marks, which is treated as a number. This may not seem like a big deal, but again, computers are dumb, and if you try to do math with a number in quotation marks, it will return an error because the computer doesn't understand that you're trying to perform the operation on a number, and it thinks you're trying to add an integer to a string, which is a big no-no in programming when you're adding numbers. So when you're programming, make sure to make a mental note of whether or not you want to make something an integer or a string, because that type of stuff makes a big difference. Alright, that concludes our segment on the base power of computers.
Now next up, we're going to be covering one of the most important components of computer science, so make sure you pay attention, because next up we're going to be discussing variables, what they are, and how we use them. First of all, what exactly is a variable? A variable is simply something that can store information and can be referenced and manipulated. Think of variables like a cardboard box. Cardboard boxes serve as a means to store items in them, which can be changed out, replaced, and modified. Variables are like cardboard boxes that store information for the programmer to reference or manipulate. Each variable simply has a type, a name, and a piece of information stored inside of it. The type and piece of information will be covered next, and the name is simply a name for the variable. Think of it as writing out a label on the cardboard box in Sharpie. Now, there are many different types of variables that a programmer can use, but right now, we will just be covering what are called primitive variables, which include integers, booleans, floats and doubles, strings, and characters. We'll start off by talking about an integer. An integer, or int for short, is as simple as it sounds, a variable that can store an integer value. This includes all whole numbers from -2,147,483,648 to 2,147,483,648. Notice how I said whole numbers. Integer values can not and will not hold any decimal values, so keep that in mind when using variables. Secondly is a boolean. A boolean is a very primitive variable which can store a value of either true or false. Boolean variables can only hold these two values and are extremely useful for conditional statements, which we will cover soon. The next two types of variables are floats and doubles. Both of these variable types are floating point data types, which essentially means that these variables can store numbers with decimal places. Whereas integers values cannot hold decimal values, floats and doubles can. The main difference between the two is that a float variable can store numbers of a precision up to 32-bit, while doubles can store numbers with a precision up to 64-bit. Essentially, a double can store more decimal places than a float, so it all comes down to how precise you want the variable to be. Up next we have string variables, which are like the strings we've talked about beforehand, except stored somewhere in a value. String variables can store strings of letters, which are just words and sentences. Strings are useful for displaying text and storing input information. Strings can also be concatenated together to form combinations of string variables and pre-written strings. This can be very useful for outputting information in a readable format for the user. For example, imagine we have a string called name. The code asks for input and stores that string of text in name. To output this information to the user, rather than simply displaying their name, you can add the phrase your name is and make it into a sentence by concatenating your name is plus name plus period. This makes it easier to read your code, while also adding variability to your code, which always makes things more interesting for the end user. Finally, we have char variables. Char stands for character, and just as the name suggests, they can each hold one character. This is useful when a programmer wants to read one button press or one character in a string without